We're going to have a look here at doing a bivariate linear regression, looking to see if there's any relationship between height and weight. And if there is a relationship, we then want to be able to model it using that linear regression option. So this is the data set is the pulse data set that's in the Minitab data library. Recall this is then come from a group of students where we're recalling whether they're smokers or not, their gender, male or female, their height, their weight, and then the students were asked to rank their activity levels as slightly active, moderately active, or active a lot. The students were all asked to have their resting pulse was taken, and then some of them ran on the spot and some of them did not run on the spot for a minute, and then the pulse rate was taken again. So there's quite a lot we can do with this data set, so I'm going to be just using it to have a look and see if there's a relationship between height and weight. So first thing to do with that is to see the data on a scatter plot. So we need to be asking ourselves which is the independent and which is the dependent variable, or which is the predictor and which is the response. That's not immediately obvious with height and weight. If we look at a BMI chart, then we will put weight on the x-axis and height on the y-axis. I think here though I'm going to put weight on the y-axis because the weight can change with no change in height, but the height can't really change without any change in weight. That's my rationale for doing that. And I'm sticking to it. So we want to see if there is first of all a relationship, or if we just got a random cloud of points. And look, we have clearly got a relationship going on. There is a positive correlation of sorts, but that cloud of points are quite diffuse. So we can look at that and think, well, it's it's definitely not all the points in a straight line. So it's not a correlation coefficient of 1, but there is definitely a trend there. It's not a correlation coefficient of 0 as well. So let's get that correlation coefficient. Another thing we can see from the graph before we do that as well, of course, is that a straight line would describe that data quite well. Remember, we can't do a standard bivariate linear regression if the data follows a curve of some sort. We can still do a regression, but we just need a slightly different way in. That is more complicated. Now, in Minitab 19, the correlation menu seems to have changed a little bit. Don't quite know why they did that, but they have done. So we want to do then correlating height and weight. You go into the options. Yes, we're doing the Pearson correlation rather than the Spearman. And in the results, we can graphs. Where's it gone? Hang on. Pearson correlation. Somewhere is an option to choose whether we want, yes, statistics to display on the plot, correlations and their intervals. No, we will display correlations and p-values because that's what we've been used to. There we go. Here's that same. So again, in the Minitab now, when we ask for a correlation analysis, we get the scatter plot drop out as well. There we can see R is positive 0.76 and the p-value is less than 0.001, of course. We can now, Minitab will now do it where it will return you the correlation coefficient with its confidence intervals. It's more common to just report the correlation coefficient and its p-value. We can see we've got a strong, positive, significant correlation there. And it's of a straight line. So it really does pay to then proceed with the regression analysis. So we go into the regression menu here. Fit the regression model. My response, remember, was going to be weight, because we can have a change in weight with no change in height, but we can't have a change in height without any change in weight. So that's the rationale there. I put height in as my continuous predictor. I want to be storing residuals. Remember, when I'm wanting more diagnostics on the residuals, I want one of these 4-in-1 graphs that's going to give me lots of diagnostics on the residuals, which I'll talk you through. Okay, so here is then the overall regression analysis. the null hypothesis of this here, oh, let's move down to here. So here's an analysis of variance that's come as part of the regression analysis. The null hypothesis of this analysis of variance is that the regression line, there it is, weight equals minus 205.2 plus 5.097 times the height. That's our y equals a plus bx. Okay, so there's a and there's b. 5.097 is b. The null hypothesis of this analysis of variance is that that regression equation does not describe a significant amount of the variability in the data set. That's the null hypothesis. You can clearly see we reject it. We can see then that the regression equation as a whole gives me this degrees of freedom, adjusted sum of squares, adjusted mean squares, and f value with that p-value, which recall is not 0, it's less than 0.001. That's all we need to say there. It's just that in this simple regression, we've only got one term in there. We've got our intercept minus 205.2, that's A. We've only got one B term in there, 5.097. So that is 5.097 times the height makes up all of the regression equation. If we were to then be repeating the analysis and maybe putting in gender or smokes into the model, these terms would appear here, and I would see if they're significant terms in the regression or not. My R squared is not the highest in the world, but it's telling me that 61.73% of the variability in weight is explained by variability in height. Here is the t-tests against A and B against the null hypothesis that A and B are not significantly different from 0. And we can see that both of them, the p-values are very low, so we're rejecting the null hypothesis, and we can say that both are significantly different from 0. The next thing we need to do then in the regression analysis is go and look at the residuals. Remember, the residuals are how much each observation, that its vertical distance above or below the regression line. Okay, and we're wanting to see with those residuals, wanting to see these this 4-in-1 plot here. So this is showing me that the residuals are approximately normally distributed. On this probability plot, they're following that red line more or less. Yes, we expect the tails to kick out a little bit. This is the histogram of the residuals, so it's a bit taily. We've got a bit of an upper tail kicking out there, but hopefully the sample size is nice and large, so we're not going to have any significant departure from normality. We'll get good old Anderson Darling to do that for us. This is the residuals plotted against every value of x, so plotted against each value of height. What we're wanting to see here is there isn't any bias. We're not seeing for particularly tall people, maybe they've got particularly large or particularly small residuals, or maybe for very small people, they could have got large or small residuals. No obvious pattern exists, which is good. The last one is very useful if the data in the worksheet down here is in time order with which it was recorded. Imagine all of these students in this class all queued up. Now, there's about 120 of them or something, I think. How many have we got? No, I've overcounted a bit. There is 91 of them. Imagine all 91 of those students all queued up, and they're having their height measured and their weight measured. Let's imagine maybe there's a systematic bias being introduced in the scales. The scales are starting to read maybe too high or too low, so we're starting to see with the observation order the residuals could start tailing down here or going off up in that direction. We're seeing a systematic bias with time order. This is particularly useful in seeing if we've got any measurement error in our data set. It is utterly dependent on the data being in time order with which the observations were made. If that's all jumbled up, or if it's in maybe alphabetical order of student, or it's girls first then the boys, and we've lost that observation order, then this graph is completely meaningless. So be careful with that one. Last thing to do then is to do our graphical summary, and we want to just be checking the residuals for normality, and we can see, look, yes, there is a tail, there is this upper tail kicking out here, but it's not giving us a significant departure from normality. And we've got this big sample size of 91, so we can have we can be very confident. There's a very high power in that Anderson-Darling test when the sample size is so high. So we've got no violations to our regression analysis.